Welcome to this explainer. All right, so today we are setting up what is arguably the ultimate scientific detective story. We're going to dive right into the bizarre nature of light as a wave and particle mystery. Look at the completely wild behavior of tiny particles and see how they literally force us to question the very fabric of reality itself. I mean, think about this for a second. How does a lifeless electron actually know that someone is watching it? Now, you might be thinking I'm setting up a scene from some sci-fi movie here, but I assure you, no way, I am not. This is a real documented mystery uncovered by incredibly rigorous scientific experiments. It's this mind-bending phenomenon where matter actually changes its physical behavior simply because it is being observed. Section 1. The Great Light Debate. Okay, let's dive into this by turning back the clock a bit. To understand this modern mystery, we first have to investigate the earliest suspects in a massive historical debate over a very fundamental question. What exactly is light? Back in the 1670s, Sir Isaac Newton argued his corpuscular theory, basically saying light is just a stream of tiny bullet-like particles. But around that exact same time, Christian Huygens proposed a completely different idea, that light was actually made of waves. Now, Newton was a total superstar of his era, so his particle theory dominated for a long, long time. But then, in 1801, Thomas Young performed this breakthrough double slit experiment that changed everything. And a century later, in 1905, Albert Einstein arrived with a massive plot twist. To really grasp what Thomas Young discovered, let's lean on a familiar analogy. If you fire physical particles, let's say bullets, through two narrow slits in a wall, you'd totally expect them to just hit the back wall and form two straight lines, right? Makes sense. But if you pass a wave, like a wave on the surface of a pond, through those exact same two slits, the wave splits into two new waves. When those two new waves overlap, their peaks add together to make bigger peaks, and their peaks and troughs kind of cancel each other out. This creates a scattered, alternating pattern of bands called an interference pattern. Well, Young fired light through two slits and got an interference pattern. Boom! He proved light was a wave. Section 2. The Double Slit Mystery. So, case closed, right? Light is a wave. Well, actually, scratch that. Not quite. Let's jump to the 20th century, where our mystery escalates way beyond just light. Suddenly, the very physical matter that makes up our universe becomes the prime suspect. Remember Einstein's plot twist? In 1905, he won a Nobel Prize for proving that light actually traveled in discrete packets of energy called photons, which are essentially particles. But wait, Young had already proven light was a wave. This massive contradiction forced the scientific community to accept this totally bizarre concept, wave-particle duality. It's the idea that light and matter exhibit both wave and particle properties at the exact same time. Now here is where things get really wild. It's one thing for energy, like light, to act as both a wave and a particle. But what about actual, tangible, physical matter? In 1961, scientists performed the double slit experiment using electrons, tiny physical chunks of matter. Instead of forming two neat lines like bullets, the electrons absolutely shocked the world. They produced a wave-like interference pattern. Physical matter was acting like a wave. So scientists thought, okay, maybe the electrons are just bouncing off each other. To test this, they did a single particle double slit experiment. They fired the electrons one by one, with plenty of time in between. Since a single electron can obviously only go through one slit at a time, there should be absolutely no other wave for it to interfere with. Yet, slowly over time, the interference pattern built up again on the back screen, which completely forces us to ask the seemingly impossible question. Could a single electron be passing through both slits at the very same time to interfere with itself? Section 3. The Observer Effect. To answer that impossible question, scientists realized they had to catch the particle in the act. Welcome to the stakeout phase of our detective story. It's time to outsmart the system. In the 1980s, they set up the which-way experiment. They fired a single electron, but this time, they placed a detector right at the slits to see exactly which path it took. But the very second they did this, a bizarre twist occurred. The electrons stopped acting like waves. The interference pattern completely disappeared, and the electrons just formed two straight lines on the back screen, exactly like bullets. And this brought about the formulation of the observer effect. It means particles behave differently when they're observed versus when they're completely unobserved. Now, the initial assumption by the scientific community was actually quite practical. They figured, well, the physical detector must just be awkwardly bumping into the electrons and disturbing them, kind of physically forcing them to change their behavior. Section 4. Spooky quantum entanglement. And this brilliantly illustrates the absolute lengths to which physicists will go to find the truth. Because if the detector was physically disturbing the particle, they needed a way to spy on the path of the particle without ever touching it. To do this, they used a loophole that relies on a part of quantum mechanics Albert Einstein famously referred to as spooky. He had profound skepticism about this particular quantum weirdness, and the historical tension around this is just absolutely fascinating. So the crucial concept here is quantum entanglement. It's a phenomenon where two particles become perfectly linked. Think of them as quantum twins. No matter how far apart they are in the universe, measuring the state of one instantly tells you the state of the other. Scientists designed a brilliant workaround using these quantum twins. They fire a photon through the slits, and right after, a special crystal splits it into two entangled twins. One twin, called the signal photon, continues untouched to hit the back screen. The other twin, called the idler photon, bounces off a mirror into a completely separate detector. By measuring the idler photon, they know exactly which path the signal photon took, but they haven't laid a finger on the signal photon at all. So what happened? The interference pattern still vanished. Even without being physically disturbed, the signal photon somehow knew its twin was being watched. So they pushed it further with a variation called the delayed choice. They moved the detectors for the idler photon much further back. This meant the untouched signal photon would hit the back screen long before the idler photon ever reached its detector. By the time the signal lands, it has absolutely no way of knowing whether its twin will be measured or not. Yet, incredibly, the interference pattern still did not appear. This leads to a wildly debated concept known as retrocausality. Since the signal photon lands before the idler is measured, the results wildly suggest that measuring the idler photon in the future somehow altered the signal photon's behavior in the past. Now, lots of scientists strongly debate whether this experiment actually proves retrocausality, but what is absolutely undisputed is that distance and time do not break the connection between these entangled particles. Section 5. Erasing reality itself. All right, take a deep breath because we are pushing the mystery to its absolute limit with the delayed choice quantum eraser experiment. Scientists added something called the eraser circuit. They used partially silvered mirrors that randomly either reflect the idler photon or let it pass right through. If the photon reflects into detector A or B, the scientists know exactly which slit the original photon came through, but if it passes through the mirrors to land in detectors C or D, the paths get completely scrambled. The information about which slit the photon came from is permanently erased. Now, what's really interesting about this slide is the result of that scrambling. When the idler photon lands in detector A or B, meaning we know for sure the path it took, the corresponding signal photon acts like a particle, no interference pattern. But when the idler lands in C or D, meaning the path information is completely erased and lost to the universe, the corresponding signal photon magically acts like a wave again, and the interference pattern completely returns. This right here is the mind-blowing climax of the explainer. It proves that the detector wasn't physically bumping the particle at all. It is the mere availability of information that collapses the wave function. If the universe has the information about which path the particle took, it acts like a particle. If that knowledge is erased or completely unavailable, it acts like a wave again. So, resolving our historical detective story, Einstein, despite his incredible brilliance, was actually wrong about this spooky behavior. The founders of quantum mechanics, Niels Bohr and Werner Heisenberg, predicted exactly this. Measurement and information truly do cause the wave function to collapse. But here is the greatest twist of all. As for why the universe works this way or exactly how information changes matter, nobody truly knows. It remains an entirely unsolved mystery. We are quite literally left with a universe far stranger than fiction. I want you to just look around for a second at your computer, your smartphone, all the modern technology you use every single day. It is all powered by technologies built precisely on these bizarre quantum rules. So as we wrap up this explainer, I have to leave you with one final, deeply profound question to ponder. If the very building blocks of matter change depending on whether or not we have information about them, what is reality, truly?